So I'm going to talk about sharp isoperimetric inequalities on the Hamming cube. And a few of you might have noticed I've given a talk with the same title in an earlier workshop in this program, but this is a different talk, okay? So I'm going to talk about a totally different aspect of this work. So there's a joint work with Bologna Ludwig and Swili. That was the focus of my previous talk, but today I will actually not so much be talking about what's going on in this paper, but more about something that we needed to use. So, what is it that I want to do? So, I have a subset of the Hamming cube. So we imagine n to be a really large number, a to be any subset, and I want to fix the volume. What do I mean by volume? It's just a normalized count of vertices in this subset. And just to fix some notation, I'm also normalizing things so that this is exactly the expectation of the indicator function A. And I want to fix this. And I want to ask, what is the smallest possible boundary size of A, right? What is a boundary size? There are several different ways to define it, of course. Maybe the most immediate one is to take something like a vertex boundary. So there's also a few different variants, but let's take this one. So we're taking all the points in A, all the vertices in A, so that there is a bit that we can flip to take it outside of A. Right? So this is the vertex boundary. So it's a nice question to ask, very natural. Fix the volume, what's the smallest possible size of, smallest possible volume of the vertex boundary. And this was, of course, done a long time ago. Harper, in the 60s, said you should take A to be a Hamming ball, and you're going to get the minimum possible value. What is a Hamming ball? So a Hamming ball is a set of the following form. You take all the vertices where you sum up all the bits and you check that it is smaller or equal to a given threshold, like K. Okay? It looks like a ball. This is a Hamming ball. So let's do a quick computation, or rather I'm going to pretend like I'm doing a computation. So let's take K to be n divided by 2. Let's say n is even. The volume of A is 1/2. What is the volume of the boundary? So what's the boundary of this set? It's when you replace the smaller equal by an equal, right? So now I have to count how many elements does it have. And you see relatively quickly, you can flip any of the n-half zeros to ones, and then you're outside, right? So how many ways are there to do this? This many ways. And you can work this out. This is roughly n to the minus 1/2. So this goes to 0 as n goes to infinity. This is somewhat disappointing. Because what we would really like to have is a kind of isoperimetric inequality for the boundary size of A that is independent of dimension. Of course, we could fix this deficiency by renormalizing, but we would have to renormalize in a very unnatural way somehow. So this is somewhat not very satisfactory. So there are other ways of measuring boundary size, right? So let's measure instead, let's take into account the number of ways, the number of bits you can flip to go outside. So let's count edges, boundary edges. So for any vertex x and for any set A, I want to define this function. This function is extremely important for you to remember for the rest of the talk. Otherwise, it's going to be very, very boring. So this is simply the number of bits that you can flip so that you land outside of the set, assuming that you are starting inside of the set. Okay, so we're setting it to the number of bits that can be flipped to get outside, if x is an A, and if x is not an A, it's just 0. Okay, so it's kind of a one-sided edge boundary. All right, so now how do I make this a measure? I can take expectation of this, right, the average value of this quantity. By the way, this is equal to the expectation of HA complement. So now we're just, so the expectations are equal, but at each point they may have very different values, right? So, and what this is just a number of total boundary edges, right? Up to a normalization. So this measures the number of boundary edges. And again, I can ask what is the minimizer of this quantity when the volume of A is fixed, right? And this question has been studied, of course, also in the 60s and 70s, and maybe I should go here so that the people in the back can see better. So there's a number of names attached to this. I think there's also a problem that things were proved many, many times by different people, and so this list is incomplete. But I'm just going to write down a few. 60s, 70s. I apologize if there's a name I'm missing here. I'm sure there are more names that are relevant. So one inequality that one can prove is the following, and you will notice it does not depend on the dimension n. So you can show that for the classical isoperimetric inequality, we have this inequality where this mysterious star just means the min of x and 1 minus x. Okay, so it's this triangle function. So why do we see this mysterious function here? So this inequality is interesting because it becomes an equality. So first of all, it's independent of n. That's interesting. But it's also sharp because there's an equality if A is a subcube. So what do I mean by a subcube? Exactly what you think. I mean, it's a set of this form, set of all vertices, such that you fix some coordinates, right? You fix some bits. So let's fix the first k bits. Let's set them to 0. Then this thing has volume 2 to the minus k. So, for instance, maybe the most important case to focus on for this talk is k equals 1. Then we take exactly half of the bits, and we get half of the volume. So what's the boundary of this? This is a very, very different set from the humming ball, right? So the humming ball... No. It's codimension k, right? Because there's a normalization factor in this. There's 2 to the minus n here, right? So that gets rid of that factor. So it's 2 to the minus k. What are the boundary vertices in the set? Every point is a boundary vertex, right? So it's terrible at minimizing the vertex boundary. But it turns out to be optimal at minimizing the edge boundary. And the humming ball turns out to be terrible at minimizing the edge boundary. So there, if you compute it for the humming ball, you actually get that it goes to infinity with it. Okay, so there's something mysterious here. There's something weird going on between these two kinds of examples. And there's something in between that we would like to understand. Okay, so before I get to that, I want to point out one more thing. So not every set, not every possible volume can be the volume of a subcube, right? It's only volumes of the form 2 to the minus k. So you could ask, what happens if the volume is not of this form, right? Then it can't be a subcube, so what is it? Also in that case, we know actually, we know the complete answer to this minimization problem. So if A is of the form m times 2 to the minus n, so this is the general form, right? Volume has to be of this form. This is saying just that A has m many vertices in it. Then minimized by, so I can just take m vertices in lexicographic order. And an elegant way to write this down is just to make a bijection from natural numbers, or from a subset of the natural numbers to the vertices of the cube, which is realized by binary expansion. Okay, so every vertex here, every natural number here corresponds to its binary expansion. That gives me a vertex in the hypercube. This is the set. Very simple. And you can compute what is the value of EHA, and you get a beautiful fractal graph in terms of the volume of A. And there's more on that pictures in my other talk. So we completely understand the answer in both of these settings, right? And somehow, so this answer here is not very satisfying because we don't understand where did the hummingballs go, right? So there should have been, would be nice to have a continuum where we see where the hummingballs get lost, right? So one can do the following. We can introduce a parameter. We want to make more boundary measures, okay? We want to understand what happens in between. And so I'm going to set this up so that one endpoint is the vertex boundary and the other endpoint is the edge boundary. So you can just do this, right? So now, what happens if beta is equal to 0? This is the vertex boundary. The support of this function HA is exactly the vertex boundary of A. And here you have hummingballs, right? Now if beta is equal to 1, you have edge boundary. And here we have subcubes, or these complicated sets. So what's in between? So we can do one easy calculation. We can just plug in the hummingballs and see how they perform, right? So let's plug in hummingballs. Let's take the hummingballs of half radius. Okay, so they have half the volume. So again, A is 1/2. Now, what's the expectation of HA to the beta? Well, this is actually, it turns out, a constant function. So if you're on the boundary of the hummingball, then you take exactly an equal value, and the value is n divided by 2. I have to raise it to the power beta. And now I have to multiply by the support. And the size of the support is something we computed already. There's a constant here, so let's do roughly. So what is this? Roughly n to the minus half plus beta, right? So what you notice immediately is that if beta is anything smaller than 1/2, this will again go to 0 as n goes to infinity, right? So hummingballs are still really good at minimizing this quantity, right? But something funny starts happening as soon as beta is greater or equal to 1/2. So in particular, if beta is equal to 1/2, this no longer goes to 0. So you might ask, are there some other examples that make this thing go to 0, right? Is there a better minimizer than the hummingballs? And the answer is, we don't fully know if there are better sets, but we know that there is a lower bound that's independent of it. So Talagrand, in the 93 paper, proved, among many other things, and this was not the main thing he was after in this paper, but this is one of the things he proved. This is wonderfully simple inequality, that the expectation of the square root of HA is greater or equal to square root of 2 times volume of A times 1 minus volume of A. Okay? And this is beautiful and surprising because it is independent of A. Okay? So this says that you can't do much better than that, up to perhaps a constant. Okay? However, in this talk, I really care about constants. Okay? So in another way, this is not a very satisfying inequality because it's not sharp. There's never a case of equality unless A is the full or the empty set. So this is not sharp at all. We would like to improve this. And there have been various improvements. There's a paper by Koff and Götze from 1999. that gives some improvement. They also do many other things in this paper. In particular, they're focusing on the p-bias case. I'm looking only at uniform measures, because I can't even answer this question for uniform measures. So then there was a paper by Beltran, Ivanishvili, and Madrid last year that further improved, in some sense, this inequality, or no, literally improved this inequality, improving this constant. And then most recently there is an improvement in our paper. Doesn't take this form anymore, but it also improves this inequality. I don't want to talk so much about what this is, but how to prove such lower bounds. Okay, so there is actually a conjecture. We started out talking about minimizers. So you might ask, what are minimizers for this quantity, right? Are they now hummingbirds or are they subcubes or something totally different? And unfortunately, the answer is I don't know, but there's a conjecture. So the conjecture is that this quantity is minimized by subcubes if A takes the volume of a subcube and beta is at least 1/2. And this is still open, but there is a lot of progress towards this. So first of all, beta equals 1 is checked, right? This is just Harper. And then there was a paper by Kahn and Park, and this is really the most important paper for today's talk, that gives us a threshold, is log 2 of 3 over 2. This is just the number 0.58 ... And they were doing this for k equals 1 and 2. So this is Kahn and Park in the year 2020. And then this was further improved to the same threshold, but for all k, by Beltran, Ivanishvili, and Madrid last year. And they were also able to lower this threshold to 0.53, but only for k 1 and 2, so for the half cube and the quarter cube, also by the same. And then in the paper with Bologna and Pata, we managed to get very, very close to 1/2, but not quite. It's frustratingly away from 1/2, but we really can't get over this threshold for all k. And exactly where this threshold comes from, that was the focus more of my other talk. Today, I want to talk about something else. So I need to clean this board. So what's important on this board to remember is only the normalization of volume that we have and the definition of HA, okay? HA is the number of edges that point outside, coming from vertex X inside. So now I need to manage this technology here, which I haven't done in a long time. Wait, what? Okay.
You first do one thing and then the other.
That's how it's meant, okay. I'm used to these two components being separate, and then you can combine them in one step, but apparently I'm not supposed to do that here. Okay. So let's think about how would we prove lower bounds for the expectation of HA to the beta, right? That's the question. How do we prove these lower bounds? And there's essentially 3 steps. And all these proofs that are on the board after Harper follow these 3 steps. The first step is you reduce this optimization problem to a different optimization problem, which involves something called a 2-point inequality. And the second step is you find a function that is a good candidate for the 2-point inequality, And the third step is you prove the two-point inequality for that function. And it's important to realize that these are different steps because they require very, very different methods. Of course, if some divine inspiration gave you a function, you could skip step 2, but typically we don't have that. So,
one question. Are there
yes.
applications for the sharpness of the constant vertex?
Applications?
Yeah.
No, I don't know. I don't really care about applications. I just want to solve the minimization problem. But it would be interesting, nevertheless, to hear if somebody thinks about it. I don't know of any. Probably in applications it never matters whether the constant is closer to 2 or closer to 1 if you already know that it's between 1 and 2, right?
Yeah, it's Poincare inequality.
Yes.
Poincare inequality is application in itself.
Yeah, but does the sharp constant matter? I don't know if it matters. Okay, it matters to me at least. So, how do we prove lower bounds? This is what I want to do for the rest of my time. How much? I have enough time. Okay, great. So, how do we prove a lower bound? And first I need to decide what lower bound do I want to prove, actually, right? And this is already where the problem starts, because I don't know what function should be here on the right-hand side. And so I'm just going to put any function that depends on the volume, right? And part of the task is to find this function, actually. And I'm calling this function b for Bellman, because this uses something called a Bellman function technique, or at least I want to call it that way. And there are 3 steps, like I explained. So the first step is an induction on n, and this will give us a 2-point inequality for b. So some inequality that involves real variables that b has to satisfy to close the induction step. Okay? And then the proof of this inequality is reduced to exhibiting a function b that satisfies such an inequality. But we don't only want any such inequality, we also want a good one, right? So actually we need to keep in mind that we want that, say, let's just focus on the half cube. So b of a volume of a half cube should be the expected measure, a boundary measure of the half cube. That's exactly 1/2. So we actually want this, right? So turns out it's not too hard to find functions that do the 2-point inequality, but they will not do well at this condition. So this is the holy grail. 1/2 equals 1/2. Okay, so this is the first step, and this is the second step is find a b, find a candidate b, and this is very, very difficult actually, because you very quickly run out of obvious candidates. They just don't work. You have to do something else. And the 3 is verify properties of b. Okay, so, and what I did last time is these 2 steps in my talk, and this is what I want to do today. The first step, okay? And this is based on the paper by Kahn and Park. But I'm hoping to illustrate a method that is much more general than just this application. It's the Bellman function method. So we do an induction, and we identify condition on some mysterious function to close the induction. I just want to illustrate this in this very interesting example of Kahn and Park. So what are 2-point inequalities? How do they look like? I'm going to give 2 examples. The first one goes back to Volkov. So Volkov in the 90s gave a very nice proof of the Gaussian isoperimetric inequality via the hypercube. This is very remarkable. And the main ingredient to this was an induction argument that where the induction step is achieved by such a 2-point inequality. And this was later also expanded on by Volkov and Goetze. So these are papers from the 90s, and I just want to write down what this was. It's a very remarkable inductive proposition. So if we take any function from the unit interval to the non-negative numbers, and if it satisfies this inequality star, which is a functional inequality, so we're going to take b of the expectation of f smaller equal to the expectation of b of f. So I'm plugging in f of x for every x over which we're taking expectation, plus some mysterious quantity mf that I will define to the beta. Okay, so for now this is mysterious, right? What does it mean? But this is a functional inequality, and we want that this is satisfied for all functions on a two-point space, so the one-dimensional Hamming cube, but importantly taking values in the full unit interval 0, 1. Then it satisfies star for all functions on any dimensional hypercube. Okay, but this is very remarkable. How do you prove it? Of course, using induction, right? I'm not going to do the proof. The proof is actually very easy once you write down the statement. So the hard part is coming up with this functional inequality in the first place. So I'm not going to do the proof of this one. But now let me just explain. Okay. Let me just explain why this. Maybe I can do that while cleaning the board.
Could you define MF?
Sorry?
Define MF?
Yeah.
Yes, I should define MF. Thank you very much. So I'm going to define and then you can think about what this means. So I'm going to MF is kind of a version of a gradient, essentially. So I'm going to define MF to the power instead. And we're summing over the coordinates. And we're doing f of x minus f of x ith bit flipped, right? This means flip the ith bit. And now we're taking the positive part, that's very important. And we're raising it to the power 1 over beta. You can think of beta being 1/2, and these are squares, right? Okay, now think about what happens when we plug in the indicator function of a set A for f. Think about what happens to the function inequality while I clean the board. So, anyone? What do I get if I plug in f equals indicator function into the function inequality? What happens?
Isn't it h?
Yes, I get a familiar quantity, and that also justifies this funny definition. So, if I plug in f equals indicator function, then star becomes equivalent to, so okay, what is the expectation of the indicator function? It's the volume, so it's b of volume of A smaller equal to expectation of this stuff, okay? I lied to you a little bit. I also want that b of 0 and b of 1 is equal to 0. This is a necessary condition, not for this proposition to hold, but for the lower bound that we want to prove to hold, right? Because plug in the empty set or the full set, you get 0 on the left, so you better get 0 on the right. Okay, so this better be true. And now if I plug in the indicator function only takes values 0 and 1, right? So this b of f to the power will just disappear. And I'm only left with m. And it turns out that m of indicator function to the 1 over beta, let me just not write this power, is exactly HA to the beta. Okay, and why is that? Because now imagine you are in the set, x is in the set A, right? This is indicator function of A. X is on the boundary, but it's inside the set, and this will be 1. And this will be 0 for as many coordinates as you can flip so that you get outside. So this is exactly HA of x many coordinates. And we're always raising 1 to the power 1 over beta, right? And this plus here ensures that we're not counting vertices that are outside the set that we can flip to get inside the set, right? So we're exactly counting this one-sided boundary measure. If we remove the plus, we get something closer to a discrete gradient. That's also very interesting. So hopefully I've convinced you that this is true. And so what we get here is expectation HA to the beta. It's exactly the lower bound I wanted, right? So now I've reduced proving this lower bound to proving this function inequality for n equals 1, right? That should be easy, right?
So why is HA to the beta? Don't you also take 1 over beta out?
Yeah, but it cancels.
Okay. The beta is inside the expectation. Okay.
Yes.
Okay.
Yes, exactly. So the BF, this is 0, and so this cancels. 1 over beta, beta. Okay. So what happens when n is equal to 1? We should write this down, right? This is the golden two-point inequality. So then f only takes two values. Let's call them x and y, okay? So let's also assume that x is smaller or equal to y. This is no loss of generality by symmetry. It's completely symmetric. So f of 0, f of 1, right? Now let's evaluate this expression. So we get, let me write this down up here so that everyone can see it. So we get x plus y divided by 2, e of f, right? The average of the two values, smaller or equal to, so this expectation of a 2-point space, so we're just going to evaluate both of the points. Plug in the 0 bit, plug in the 1 bit. When we plug in the 0 bit, what happens? Well, we get b of x, the first part, and the second part, we actually get 0, right? Why do we get 0? Because this evaluates to x, this evaluates to y, and x was smaller than y, so this is negative, and the plus destroys it. So it's 0. What happens to the other bit? In the other bit, it stays alive, and we get b of y to the 1 over beta plus, now this evaluates to y, this evaluates to x, and it leaves, there's a power, 1 over beta, the plus does nothing, we raise it to the power beta. Okay? So we get this beautiful inequality, right? This is very nicely symmetric. It looks very similar to Bobkov's famous two-point inequality that he used in the proof of the Gaussian isoperimetric inequality, but not quite. In that inequality, this term was replaced by a term like this, and that's because there was no plus. Okay? So this is beautiful. Unfortunately, now you can try to do step 2 and step 3, but somehow it's we lost too much when we did this, turns out. You need a slightly better two-point inequality than this to get the results that I quoted. Okay, so we got a beautiful inequality, but we need to improve it a little bit.
You
So-
mean because it's difficult to go to n to make induction? Well, why we need different? Because
Well,
to make induction or what?
No, the induction is done, right? So it's definitely true that if you have a b that satisfies this, and b of 1/2 is equal to 1/2, then you get a subcube inequality lower bound. But the problem is we're not going to find a b that does that.
So you want to maximize the value of b at some particular point? This is the optimization you
No.
or you
No,
want?
this always involves all the points of b at once. So we cannot look locally at one point. So
Yeah, but when you eventually want to show a local bound for h of a to the beta,
sorry, a local bound?
what b are
No,
you?
no. Once I have this, I get this. This is what this proposition shows. Once I have this, I get this. But the problem is, it's very hard to get this. So the plan is, I'm going to make my life a little bit easier by making this inequality more complicated, but easier to satisfy. So I'm going to increase the value of the right-hand side. Okay, that makes it easier to satisfy this inequality. Okay, so this is the key in the work of Kahn and Park. So
Sorry, what is the b of f in the star? B of f.
yeah, b
on the
of
right-hand
f
side.
is b of f of x, right? So we're taking expectation over x, and b of f just
okay,
means
okay.
b of f of x. Okay. So Kahn and Park in 2020, they somehow refined this inductive procedure. There's one thing that you can easily see might be an indication of why we lose something, right? Because we need to prove something for functions that take values in all of 0, 1, right? But we're actually only interested in plugging in indicator functions. So somehow we should redo this induction argument, making use of the fact that these are indicator functions, right? Then we don't get a nice functional inequality of this shape, but maybe we get something slightly better. And this is what Kahn and Park did. And they didn't quite formulate it this way. I learned this formulation from Pata when he explained this argument to me. So this is what I'm going to present. So Kahn and Park said that if b of 0 and b of 1 is equal to 0, and yeah, b is again some function, I'm not going to write down any function that has this property, and it satisfies this inequality, x plus y divided by 2 smaller equal 1/2 b of x. So it looks very strikingly similar, but now I'm going to increase the size of this term by a little bit. And the functions, one can see, once you finish with step 2 and step 3, you see that the functions you get in the end, they actually make use of this part here. So it's going to look very mysterious, but this is the nature of these optimization problems. The answers are not always pretty. So this is a second term, right? So we've just replaced this by a max, we made it bigger, we made it easier to satisfy this inequality, so hopefully in step 2 and step 3, step 2 will be easier, it will be easier to find a candidate, but step 3 will be much harder because now you have all this mess to deal with, right? Okay, anyways, so we need to have this for all x, y smaller or equal to 1, and then we have our lower bound greater or equal to b of volume of A. Okay? So now in the last 20 or 30, how much time do we have? 30 minutes? In the last 30 minutes I want to prove this proposition, okay? And that's really the core of my talk. And the upshot is again induction on n. And there's exactly 2 points in the proof where you need to do exactly the right thing, and the rest is autopilot in some sense. So
is there any equation for the first 2 point inequality?
This is a very good question. So if you symmetrize this inequality, then there is a very intuitive proof via stochastic calculus that somehow interprets this as a random walk. I don't know of such an interpretation for this asymmetric version. Would be nice to look back into that and try to see. But we're going to see how both of these terms come up in the induction. So they come up in a natural but not very satisfying way in the induction. Natural in the sense that this is just what you get when you do the natural thing. And not satisfying in the sense that you don't understand why this happens. At least I don't. Okay, so how to do this argument? So it's all very elementary, but not easy. So the proof of this. Induction on n is the plan. Okay, so what am I going to do? So I'm starting out with a subset of the hypercube in n plus 1 dimensions, right? And now I'm going to assume that I have this proposition, which I erased. Okay. Let me just write down the goal. The goal is the most important part. The 2-point inequality you don't need to remember because we're going to derive it, right? So if you start with this proof not knowing the 2-point inequality, you will do the same thing, right? You just enter it at the end when you're done. So the 2-point inequality is just the thing that makes the induction step work. We're going to try to see what that is. Okay, we're trying to prove this for a function b. Okay, by induction on n. So we have this, and we are assuming that we have this inequality for all a in a lower dimensional cube. Okay, so we're going to need to produce by this. We're going to need to produce lower dimensional sets from this higher dimensional set. What's the easiest way to do that? Let's slice off a bit, right? So that's exactly what we're doing. And that's the first very important step. So I need to introduce some notation so we don't get confused. So a point x will be in the higher dimensional space, and I will write its coordinates as x prime for the first n coordinates, and then xn plus 1 for the last coordinate, okay? And so this a0 is supposed to live in the lower dimensional cube, so it's going to be the set of x primes in 0, 1 to the n, such that x prime comma 0 is in A, right? So I'm just looking at the vertices that have the last bit equal to 0, and I'm slicing the last bit off to get a lower dimensional set. And now I do the same for the bit 1, and now I get two nice subsets of the n-dimensional cube, and it's very important to realize that they may intersect very heavily, right? For instance, just take a subcube, then they will generally be equal, or one will be the empty set and the other one will be the whole thing. So these can intersect very heavily. In particular, they can be equal, A0 and A1. It's important to keep in mind. Now what do I want to do next? So I want to use my inductive hypothesis. So my inductive hypothesis tells me that, well, now I have lower dimensional sets, so I can apply inductive hypothesis, and I know that this is true. Let's write I will be 0 or 1 for the rest of the talk, okay? So we have this, right? By inductive hypothesis. And now, what do I want? It's also very easy to write down what I want. What I want is the same inequality for A, right? And so what would be the first thing nice to figure out? What is the volume of A in terms of the volumes of A0 and A1? It's just the average, right? So it's B of A0 plus A1 divided by 2, the average of the volumes. This is factor 1/2 because there's a normalization and we're moving from an n plus 1 dimensional volume to an n dimensional volume. Otherwise it would be just a sum. Okay, so now how do we get from this to this? Well, we need to take a look at HA, right? And just write it in terms of HAI. It's very automatic from this point. So, and this takes a little bit of an effort. So I need to draw a picture to explain this well. So here's a picture of A0 and A1. And as I said, they could be intersecting a lot. They might also be completely the same. There's one more thing I want to draw in this picture, and it's the support of the function HA0, so the boundary of A0. The boundary of A0 is a subset. I'm going to call it B. So what is B? Bi is just going to be the support of HAI. It's the same as the boundary of AI. And it could also intersect with A1. Okay, so now let's see what happens to this quantity. So we need to analyze this quantity, HA beta. So what's the first step we should do, right? There's only one thing we can do. Split it in terms of the last bit, right? There's really only one thing you can possibly do here to make progress. So you split it in terms of whether the last bit is 0 or 1. Okay, so now let's take a look at this term, simplify it in a certain way, and then do the same to the second term, okay? Let's focus on this when the last bit is 0 for now. So let's try to analyze what happens to HA when the last bit is 0. So it's going to be a point, we're plugging in a point of the form x prime comma 0. Okay, so how do I simplify this? There's no need to think, this can be done by a computer. You just write down the definition. So this is the number of coordinates such that x prime comma 0 bit flip ei is not in A multiplied with indicator of x prime comma 0 in A, right? So I've just mechanically copied the definition, okay? And now I can realize this is actually the definition of A0, right? And here there's a product structure, so this splits into two terms. I can count the first n bits and then I count the last bit. So if I count the first n bits, then the 0 here is gone, and I'm just looking at counting bit flips in A0, so I just get A0 of x prime, okay? And for the last bit, what do I get? Is, well, I have to check. So in the last bit, when I is equal to n plus 1, then the 0 will be flipped to a 1. This is exactly the definition of A1. So what this means is that x is not in A1, right? X prime is not in A1, okay? And then I still need to remember that x prime had to be in A0, okay? So together, the product of indicator function becomes this. X prime is in A0 without A1, right? And now we realize that this function here, so this is the function we need to understand. Remember, this will be raised to a power beta. So we need to understand exactly when these two terms are non-zero, right? But it's very natural to distinguish these cases, right? And there are 3 such cases. So there are 3 cases where this quantity is not 0. Either this is not 0, or that is not 0, or they're both not 0, right? These are the 3 cases. So let's just write down these 3 cases. So what are the 3 cases? So when is this not 0? HA0 of x. When is this not 0 and this is 0? Okay, so we need to be in the support of HA0, so we need to be in this B0 set. And we need to be in A0 without A1, right? So we need to be in A1, right? So we need to be in this set. And this is where I wanted to use colors. So, okay. You need to be in this green set. You need to be in the green set. So if x prime is in B0, intersected A1, right? And now, what happens? When is this equal to 1? It is equal to 1 if we are not in the support of this function, and we are not in A1, right? So this is exactly this yellow set. Okay, so we are not in B0, and we are not in A1.
Sorry for the first, you mean H plus 1, the first line.
Yes, this is HA0 x prime plus 1 with a condition.
Below, on your computation, the first case is. The first case is.
The first case is HA0 of x prime.
Plus 1.
No, not plus 1, because here x prime is in A1, and this is only 1 if we are not in A1. Okay? It's very important I don't make a mistake here, otherwise it's going to be messed up completely. So please keep giving me such doubts. So here we have B0, but not A1, right? This is the one case. See, I already made a mistake. This is A0 without B0 union A1, right? That's what this says. Okay, and now the last case, do I have another color? Blue. This is the case we are most annoyed about. It's when we have both terms, because they're going to be raised to a power beta, right? So that's annoying. And this is where we're going to lose something in the argument. This is this remaining set. This is when we are in B0, but we are not in A1, right? But that's when both of these terms are going to be non-zero. So x prime is in B0, but not in A1. Okay. And then I guess there is the catch everything else term, right? So it's 0 if any other thing is true. Okay, so these are nice 3 disjoint sets. We need to understand 3 contributions. And we are still in the part where everything is automatic, right? So we haven't had to do anything really, other than come up with a plan of doing an induction and doing it by slicing a coordinate. So nothing really has happened. This is just what happened and what is there. I'm just writing down what is there, even though it looks a bit annoying. Okay, so now let us write this term out, unfortunately. I'm only going to write out the set for the 0 bit, when the last bit is 0, and when the last bit is 1, it's the same term. Okay, so now what we have is that 1/2 E H A to the beta 1xn plus 1 equals 0 is, why is there one? There's no 1/2. There's no 1/2 here, the 1/2 will come here. So now we're switching from an expectation in an n plus 1 dimensional space to an n dimensional space, so we pick up this factor of 1/2, and we're going to decompose according to these three cases. So we have HA0 to the beta indicator function of B0. Please catch me if I make a mistake here, otherwise we're going to have a big problem. So this is the green function plus, okay. Then there's a 1, so I can resolve that expectation to just the volume of the set. A0 without B0 union A1. So this was the yellow term. This is the yellow contribution in the picture. And now we have the complicated term, where we have HA0 plus 1 to the beta with an indicator function of B0 without A1, and this is the blue term. Okay? And then this is just a 0-bit term, there's a 1-bit term that looks the same, right? And the sum of them we want to lower bound by B of average of the A0 volume and A1 volume. Okay, so what next? Now we need to worry about this finally, right? We need to face the problem. And there are probably several ways to do this, but there's only one way, I think, that to do this in a way that works. And this is to invoke the following. So, of course, we're going to use convexity, right? But how exactly are we going to use convexity? So I'm claiming that expectation of f plus g to the beta, that's exactly the kind of animal we have, right? So we want to rewrite this in the form EF beta to the 1 over beta plus expectation g to the beta 1 over beta to the beta, okay? I'm claiming this is true. If beta is smaller or equal to 1, so maybe just replace beta by 1/2 and then you will see. Why is this true? Maybe to convince you, I can rewrite this as the expectation of a norm. So this is the same as expectation of the 1 over beta norm of this vector of two-dimensional 1 over beta norm. Okay, this is the same. Just by replacing f by f to the beta times 1 over beta. And this side, on the other hand, is the same expression with the norm and expectation switched. So it's expectation of this two-tuple, f beta, g beta, so expectation x on a two-tuple component-wise, 1 over beta. And now what I'm claiming here is just a triangle inequality, right? Which we know is true by convexity. So, okay, so this is something I am allowed to do. So, great. Can I erase this? I think I can, let me erase it after I've applied it, okay. So I want to apply this inequality to this term, right? So, okay, so there's a 1 of these functions is 1, say f, and then I get simply expectation of a constant, so it evaluates as volume, to the 1 over beta, plus thing that I'm left with, and it is expectation of HA0 to the beta. And we're very happy to see this, because this is something that occurs in the inductive hypothesis, but it's still multiplied with an indicator function. It's a bit troublesome. And it's raised to a power 1 over beta, and the whole thing is raised to a power beta. Okay, so we have this. So this term is greater or equal to this, right? Right, so now it's time to give names to things. So maybe let me introduce names on this board. Clean this. So the idea of the Bellman function technique, so this was the first step where we might have lost something, okay, right? It was an inequality. The next step is also some step where we might lose something. We are going to identify, so there are very many high-dimensional quantities in here, right? Like there's the there are these sets A and B, and they are subsets of a high-dimensional cube. We don't really understand this stuff. What we do understand better are real numbers. So, or inequalities of real numbers. This, at least we have the illusion that we understand this a bit better. And that's the idea. We want to reduce to an inequality just of real numbers. So we basically want to replace some quantities here by just real numbers and capture the constraints that they have based on what these real numbers were. And then that is going to become our two-point inequality, hopefully. So to do that, I need to define real numbers. And this is really a place where you make choices. And it's important you make these choices correctly. So how do we make choices? So this is our term of interest. So let's start by giving names to things that we know definitely appear, right? Like volume of A0, volume of both of those. And then I also have a feeling that the intersection is going to be important. So I'm going to give a name to the intersection. That's going to be one of the relevant variables in my optimization problem.
You mean intersection?
I'm very sorry. Intersection of A0 and A1. So it's this area here. It's not colored. Okay, now let's try to look at this term and let's see what's not expressed in terms of these two. And we see a whole lot, actually. There's a lot that's not expressed in terms of these two. So maybe I need to switch boards. No, I don't. Okay. So I'm going to define this term ui to be expectation of HAI beta 1 BI A1 minus I, right? So this is exactly the second term in this bracket here. Okay, that I'm going to call that u. It's just a quantity that appears in my term, and I want to give it a name. I don't understand this quantity, so I'm replacing it by a real number. I see what constraints this real number faces, and then I hope to make progress, right? This is the idea. So I'm just going to call it something, ui, okay? Now, next thing, there is something very similar to that outside of the big to the beta. It's that one, right? That yellow term, the first, no, it's green. The first green term there, right? So the green term is the vi, EHAI beta 1 BI intersected with A1 minus I, right? And now you notice something. If you sum these two terms, then you get exactly something that's understood by the inductive hypothesis, okay? That's the sort of thing we're looking for to make progress. So this is the expectation of HAI to the beta, right? And this is wonderful good news because this is greater or equal to B of AI, right? And so this is one of these constraints that I'm talking about. This is now a constraint. If you look at both sides of this inequality, it doesn't mention anything on the hypercube anymore. It's just a constraint in terms of real numbers. Okay, and we want to kill the whole expression and replace it by things that only are real numbers. Okay, so these are u and v. So what terms do I have left? I killed that expectation, I killed that expectation, so now I have this yellow thing left, right? So there are a number of ways I could write this, I guess. Can I write it? No, actually I didn't kill the blue term yet. The blue term consisted of two things, right, after inequality. One is the expectation thing and one is this volume thing. Let's give a name to this volume. So, and that's really just a choice. So, a choice that turns out to work very well. So, I'm going to call Pi to be Bi volume without A1 minus I, right? I'm going to call this Pi. This is just some number, and it's important to record some inequalities that this number satisfies. There is one inequality I can see immediately. Bi is part of AI, so this is smaller than this. And this is something I understand, because this is exactly AI minus the intersection volume, right? So here I have, again, a constraint in terms of real numbers. And it's important to realize that this is somewhat arbitrary, right? This is, we discovered this inequality, we thought it might be useful. So the best approach at this point is basically the greedy algorithm. So we try to discover all the trivial, so-called trivial observations between these real numbers and hope that we end up with something good, okay? So is there something else we can say about P0? And this is really the key for this one. So if we don't do this next step, then we're going to end up with the same two-point inequality as Bobkov and Götze. But we need to input one more bound on Pi. So Pi is also bounded by, let me erase this. So Pi, or let me start in another way. Let me start by writing down Ui. So what was Ui again? It was this. HAI to the beta 1 BI without a 1 minus I. Okay, now let's observe that this function is actually integer valued, right? And then it's raised to the power beta. And since we are multiplying with indicator of support, BI is exactly the support of this function. This must be greater or equal to 1. So we can replace this by 1. And then we just get BI without a 1 minus I. And this is exactly the number PI. So Pi is actually not just smaller or equal to AI minus t, it's also smaller or equal to Ui, okay? And we will see in the end why this exactly gives us the improvement that we're after. So it's a very innocuous thing, right? We're just observing that something is greater or equal to 1, but you might have missed that. If you aren't careful, you might have missed that. So easy to miss things. Okay, so now I think I have all the variables that I need. So the last thing to express was the question?
Here you used the Boolean.
I used that the definition of HA as being integer valued. It's just a number of bit flips I can make.
Yeah.
And so it needs to be at least 1, if it's not 0. And it's not 0 because we're on this port.
So for general gradient, it will not work at all.
This will not work if... yeah, exactly, right. Yeah. So this is really one of those steps where we use that f is 0, 1 valued. So you cannot do this in the setting of Bobkov's inequality. So this is exactly where we win. Okay, but I still have to convince you of the fact that we win. So far, this is a mess, right? Okay, so let's reduce the mess to something less messy. So the yellow term is what's left. Okay, I've handled the expectation there, this whole blue thing I've handled. The yellow thing is what's left. So let's write down the yellow term. This is A0 without B0 union A1. And I can write this, so, okay, here it's good to look at the picture. So it's this yellow thing, right? So it's the whole A0 without the intersection, so T, and without the blue, okay? And what was the blue? We gave a name to the blue, we called it P. So it's minus P0, right? Okay, good. So now I'm fairly happy. Now I'm just gonna forget that I ever looked at this thing above and replace it by something only in terms of real numbers, okay? And let us remember what we need to do to close the induction, actually. To close the induction, you need to take the sum of this term and the sum of the one with the 1 bit in the end, and you need to lower bound it by b of average of A0 and A1. Okay? Now with that said, I can erase this. Okay. No, I should absolutely not erase this. I should first rewrite it and then erase it. Okay, now let me translate this. Let me translate this into the language of real numbers. But let me translate the whole term, right? So now the whole term that we are interested in, so this EHA to the beta, this whole thing, right, I'm claiming is lower bounded by something that's this, okay? 1/2 sum over the 2 bits, 0 and 1, just a sum over 2 elements of the first thing, we call this V, okay? This was VI plus this thing. We expanded this in terms of AI minus T minus PI, right? That's this. So this is becoming that. This is becoming that. And now the last thing, the blue term, will become this. So it is, what was this? This we gave a name to, we call it P. This is Pi to the 1 over beta plus we gave this a name, this was ui to the 1 over beta, to the beta, this was the whole blue term. Okay? So far I've proved this, right? I've proved this. And now what we want is that this is greater or equal to beta of A0 plus A1 divided by 2, right? And so I can actually claim now that I'm done. Because I can say, oh, if I have a function b that does this step here, because you notice this inequality depends only on real numbers, right? This inequality only depends on all these quantities. So how many are there? There's A1, A0, 2, there's 2 u's, 2 v's, so those are 6. There's 2 p's, those are 8, there's 1 t, so there are 9 real numbers. Okay, they satisfy some constraints, they're all written down here. And if you have that this inequality holds for all real numbers satisfying this constraint, right? It's an equality, it's a condition on the function b, it doesn't mention cubes anymore, then you can close your induction and you're done, right? Because this, in the end, this is equal to b of volume of A. Okay, so this thing becomes the thing that we want, and so what I've done is I've derived a 9-point inequality, right? This is not a 2-point inequality, it's a 9-point inequality. So, how much time do I have left?
No, it's
done.
It's 2 point, but in
Yeah.
9 dimensions.
Okay, so I have not much more time left, but I can very briefly explain you why this 9-point inequality is actually a 2-point inequality. So, you can eliminate 7 of these 9 variables. So I'm saying, okay, why can you eliminate 7 of these 9 variables? Do I have 5 more? I think we started late, so I think I have a few more.
Yeah. Let the first 3 questions be and go on.
Okay, or maybe I stop here and I explain it to somebody who's interested.
No, it's,
Yeah.
why it's 2 point in the
Okay, this is the first question. Okay. So now I'm answering the question.
You're right.
We will need some.
This I will need. This I don't need. Okay, so why is it a 2-point inequality? So I can eliminate some variables. So I'm claiming that if you just stare at this for long enough, you will eliminate the variable. So we are looking for the easiest victim. Okay, there's maybe not really. Okay, so I'm claiming that without loss of assumption, I can set pi to its largest. What do I know about pi? I know that pi is bounded by something. So pi is the condition on pi is that it's smaller or equal to min of ai minus t and ui. Okay. So I'm claiming that the worst case, so when this quantity is smallest, if pi achieves this value, okay? The worst case happens when pi is the largest. In other words, what I'm saying is, or it's enough when the left-hand side is actually decreasing in pi, and this is true. I can set this to be the largest possible value. Why? Because the function that maps p to the 1 over beta plus u to the 1 over beta to the beta minus p, right? That function occurs here. There's no other p. Is decreasing. Why is it decreasing? Just do calculus. Okay? So I can replace this. So I've eliminated 2 of the variables. Let's move on. What else can I do? I can eliminate also the variable v. So v is the next to be killed. V seems to be an easy victim because it's just appearing here linearly, right? It's not inside of some nonlinear quantity. And also the constraint on v is linear, so it seems to be easy. But so v, what's the smallest possible? In v it's increasing, right? So I should replace by the smallest possible value. But unfortunately, the constraint on v is involving u, so I can't just replace v by 0, because how do I know that I'm not losing something? Except I can, because I can actually rewrite this. So vi is 0, because if I write v plus p to the 1 over beta plus u to the 1 over beta, I can rewrite this. This is greater or equal to p 1 over beta plus u plus v to the 1 over beta. So what is this? This is just the triangle inequality for the 1 over beta norm for two tuples. And the other two tuple is the vector 0, comma v. So you should read this as 0, comma v, 1 over b norm, 1 over beta norm, okay? And then this is just triangle inequality. And so I can apply this here, and then I have a u plus v, and then I have u and v only occur in the form u plus v, so I can substitute them by one variable, and this amounts to setting v to 0, right? So now I only have u left.
Is there beta over p over 1 over beta?
Let's see.
The first line. V
Yes,
plus.
here's a beta. Yes. Okay, so this is the next step. So now I am down to 5, right? So what's next?
Wait, what about the constraints involving UI?
Yeah, I've talked about that, right? So the only constraint on UI is UI plus VI is greater or equal to something. And now I have U plus V, and I can do a substitution. I can call U plus V U. Okay, so...
Okay, so you are not treating VI as 0, you're...
Well, but it amounts to setting V to 0. So I'm saying without loss of generality, if I only have the claim with VI being 0, I can derive the full generality by doing this substitution. Okay, so...
No, but this also involves changing like the upper bound on PI, right? Because UI appears in the upper bound of PI.
No.
PI is already eliminated.
But I mean the steps...
Yes,
Like all those
PI
steps.
is... Oh, okay. The order of the steps maybe needs to be adjusted. Okay, this is a very good observation. So let's put a quotation mark in here. I'm claiming you can do this. So what is the next thing to do? So let's pretend that we can eliminate V in this way. We can talk about it later. Your point. So what about T? I want to eliminate T. So the only survivors I want in the end is A0 and A1, right? So how do I do T? I actually didn't write down the constraints on T. So what are the constraints on T? They are A0, so it's the minimum of A0 and A1, okay? And I'm getting here too many minimums. So let me also assume, without loss of generality, that A0 is smaller or equal than A1, okay? So A0 is smaller or equal than A1, so this becomes A0, and now I have to analyze how T enters in this expression, right? So I have replaced Pi by this quantity. There's a negative sign of T. Here's a negative sign in T. Pi is a negative and a negative, so it becomes a plus. But it's constant 1, so in the worst case, the two cancel and it's non-increasing in T. Here, it's definitely, again, non-increasing, because if the left part of the min is evaluated, then it's a minus T. So all in all, it's non-increasing in T, right? Is that convincing? It's non-increasing in T. So I can set T equal to A0 because non-increasing in T. So now the only thing that I have left is UI, and the only constraint that's left of UI is greater or equal to B of AI. And I can replace it by B of AI because the quantity is actually increasing in UI, right? And so now if I write down the full expression after the simplification, okay, so the last step is UI is actually B of AI. Okay, so now let me write this down. So I'm going to evaluate the sum. I killed the symmetry by making the assumption that A0 is small equal to A1. So what happens if I is 0? Okay, so as vi is 0, then a0 minus t is 0 because t is a0. p0, what was p0? p0 was minimum of
0.
a0 minus t and u0. This is 0, so it is 0. This is all 0. Okay, this is 0, and this is just u0 to the 1 over beta to the beta, so all that we have is u0. But u0 was b of a0, right? And so this is the 0 bit. Now let's evaluate the 1 bit. We have 1/2 times, so what is this? This is a1 minus a0 minus, now this doesn't simplify so nicely, I just need to write it. Minimum of a1 minus a0 and u1 plus minimum a1, a0, u1 to the 1 over beta plus u1 of 1 over beta to the beta. And that's it, okay? This is my quantity, and I'm claiming this is the same as the two-point inequality from before, because now what I need to do is to evaluate the two cases when the minimum is evaluated to the left or to the right. If it is evaluated to the left, if it is evaluated to the left, let's consider that case first, then we will get a1 minus a0, it will cancel this a1 minus a0, then here we will get a1 minus a0 to the 1 over beta, so it's a1 minus a0 to the 1 over beta, plus u1 to the 1 over beta to the beta. This is what happens when the min becomes a1 minus a0. Now what happens when the min becomes u1? And remember, this is the step that we have indicator functions. So this is this lower bound by 1. And here we get a1 minus a0, oh, and this is b of a1, right? And this is minus b of a1. This is minus b of a1. This becomes b of a1 2 times b of a. This becomes 2 times b of a1 to a power to another power. So this is 2 to the beta times b of a1 minus 1. So altogether it is 2 to the beta minus 1 times b of a1. Okay? And very importantly, this is greater than 0. So this is exactly the two-point inequality that I had before, except that a0 was x and a1 was y, right? So now what you need to prove your lower bound on EHA to the beta is simply that this holds. You need a function b that satisfies this inequality for all a0 between 0 and 1. A0 and a1 between 0 and 1. Okay, and then the whole work becomes finding such functions, and it's very hard to find such functions if you also want that they are good functions. So you also want that this is true. Does this answer the question?
Yes.
So how do you find function?
Oh, okay, so there are several functions that appear in the literature, so you can play with them. You can open Mathematica and you can just try if these two-point inequalities are true, right? You can plot it. This is how to find candidates, right? And then you have to still prove it. But this only takes you so far. So the key for our previous paper was that we actually numerically computed the optimal function. So you can easily see there's actually an optimal function that does this, because the soup of functions that do this is again a function that does this. So there is an optimal function, and you can compute it. And so you can draw a nice picture of the optimal function that does this. Optimal means the largest function that does this. And then you can try to fit that plot with functions you know. And so this approach gets you very, very close to 1/2, like I've explained in the beginning. So, and then you need to prove, so it's a very ugly function. I can write down what the function is. So the function that we used consists of 3 parts. So it's x times log 2 of 1 over x to the beta if x is between 0 and 1/4, and then there's a cubic interpolation polynomial that takes the right values at 0, at 1, at 1/2, and at 1/4. And the one miracle is somehow that this cubic interpolation polynomial very closely approximates the best function in this interval. This is a miracle. David, Jose, and Pata, they were previously already working with cubic interpolation polynomials, but they didn't compare it to the numerically computed envelope. So they were somehow not getting quite the right function. And also what they were missing is the next part. So the most mysterious part of this function is on the interval from 1/2 to 1, and there we needed to come up with a function that hasn't appeared at all. This is this function j, and what is this function j? It is defined in terms of the Gaussian isoperimetric profile. It is square root of 2 times some parameter w times the famous function I of Bobkov times 1 minus x divided by w. So what is this function I? I should at least define it. So it's the unique solution to this equation. You can write it in terms of the inverse error function, composed with the Gaussian. And what is the parameter w? The parameter w is the unique number that makes this thing continuous. So if you use that function, it's very, very close numerically to the best possible function. So that's why it looks so odd, because it's just a very weird function. And that gets very close to 1/2.